Hi, in this session, I'll talk about magnetic cooling. Previously, I've talked about how using liquid helium, you can achieve a temperature of a few kelvins, and then how using dilution cooling, you can achieve a temperature that goes down to the millikelvins. So in this topic here, I'll talk about how using magnetic cooling, you can go all the way down to the micro kelvins. So first, let's start with a paramagnetic sword. So this is the starting material that we'll look at and see how such a sword can be used using its magnetic property to achieve a cooling effect. Right, first I'll sketch out the main idea. The idea is that if I start with a paramagnetic sword, right, so that's a lump of salt, possibly in the form of some powdery form. Starting from this, the idea is that I might start from, say, temperature of a Kelvin or so, right, in the beginning, probably by putting it in a liquid helium bath, and then I would magnetize. Right, so in the beginning it's in this liquid helium bath, and step 2, we would magnetize it. Okay, so we'll put a magnetic field on it, but as we put a magnetic field on it, it will warm up, alright, as the field magnetizes the material. So we want to magnetize it isothermally, meaning that as it warms up, we want to do it really slowly to allow it time to cool back down to the same, to allow it to remain at about the same temperature, allow the heat to dissipate. So we magnetize it slowly and isothermally. Now and then, in step 3, we would then isolate this salt, meaning that we might somehow put it in a very good, we will put very good insulation around it somehow to prevent heat from coming in or going out. So we'll make it thermally isolated, and then we'll demagnetize it. Right? Now, and we'll demagnetize it. So making it thermally isolated means that we're doing it adiabatically. Right? And once we've done that, it will cool down. Right? This demagnetization will cool it right down, and after that, you have a really cold material, and it can be used to also cool down other things. So this is the idea. Now, using paramagnetic salt, however, will cool the temperature all the way down to the millikelvin. Okay, and this is really about the same as what we would get using the dilution cooling method. And then after that, after we have understood the physical principles of this cooling using the paramagnetic salt, we would then talk about how, if you change this, replace this salt by a metal like copper, for example, and make use of the same process, you can then cool it all the way down to the microkelvin. So then we change using a metal instead of the salt, and then cool all the way down to the microkelvin. And we'll talk about how that is possible. So for a start, let's try to understand steps 2 and 3. How these two steps, the magnetizing and the demagnetizing step, can actually make the salt cool down. Right. So let's think about the energy levels. Now, in a paramagnetic salt, there will be ions in a salt. All right, these are atoms with some electrons removed. For example, there will be these ions in the salt that have magnetic moments. And I'll draw a little arrow there to represent that. So a magnetic moment can be imagined like a tiny magnet. Now, I'll talk specifically about spin half salt. Means that the magnetic moment in the ions will have a spin half, like an electron. So it can have spin up or spin down, just two possible spin states. Right. And in a spin half salt, if this is placed in a magnetic field, the spin can either point in the direction of the field or opposite to the field, but there are only two possible ways it can do that, and this means that it can have two possible energy levels, and the two energy levels are given by mu B times B and mu plus and minus mu B times B, where B is the magnetic field in Tesla and mu B is the Bohr magneton. Now, the Bohr magneton is a number that you can find in the table of physical constants. Just write it down just to get a clear idea what the number is. It's 9.27 times 10 to the minus 24 joule per Tesla. So that's the Bohr magneton. And the important thing to know here is that putting this paramagnetic salt in a magnetic field will give rise to two energy levels for each of the magnetic ions. Right. So there are lots and lots of these magnetic ions. Now, and schematically, let's think of it this way. Let's imagine, all right, in the beginning when the field is say 0 Tesla, when there's no magnetic field, then there will not be two energy levels. Or the other way to think about it is there is just all these magnetic ions will be at the same energy level. Okay, there will be just the one energy level where B magnetic field is 0. Okay, it's as if those two levels are together. Alright, so you have just this one level, and there would be no field, so the magnetic moments, the direction of the tiny magnet is not aligned, so it can be up and down, it's all random. So on average there will be equal number of magnets or pointing up and pointing down. Up, down, up, down, up, down. Right. So there will be lots of these. Now when a magnetic field is applied, for example, we apply a 1 Tesla field, so this level will split into those two. Okay, and there will be in principle some of these let's see. Now some of these particles will be at the top level and some will be at the bottom level. Okay. Right. So this is what happens when we apply a magnetic field. Now notice that I've drawn the same number of particles in same number of arrows. Each of this little arrow represent a certain particle in the top and in the bottom. Now in the top level I've drawn the arrows, each arrow representing a particle pointing up. At the lower level I've drawn the arrows pointing down. That's supposed to represent the two possible opposite orientations of the magnetic moments, right, giving rise to the two different energy levels. So now, but if we know, since we know about Boltzmann distribution, we know that the higher level should have fewer particles. Now in the beginning, we can think about it this way. In the beginning, when the two levels are together at zero magnetic field, you would have the same, the particle orientations would be random. So there will be some pointing up, some pointing down, there will be equal numbers. Now initially when you apply the field and the two levels split up, you can think that right in the beginning you would still have this, all those pointing up will go to one level and all those pointing down will go to the other level. So that's why you have equal number of particles in the higher and the lower level. Right, but since from Boltzmann distribution, we know that the higher level should have fewer particles. This means that some of those particles from the higher level would go to the lower level in order to achieve this Boltzmann distribution. Okay, so this is what happens. So when we increase the field, magnetize it, that's the magnetization, we have this. And because of the Boltzmann distribution, some particles will come down. So you have now fewer particles on top and more particles below. Right. So now then, when the particles come down from the higher level, something happens. Right? Those particles at the higher level has high energies. And when they come down to the lower level, they will give out this energy. So energy is given out in the form of heat. Okay. So in thermodynamics, we think of there's an analogy between applying a magnetic field, in which we think about that as doing magnetic work on the material. And in terms of the energy levels, this is what's happening. All right, it's because particles would have to go down from the top to the bottom, so heat is given out. And this is the step which I called, which I said that we magnetize it isothermally. So what happens here is that to make this happen, we would apply a magnetic field, right? Turn up the strength of a magnetic field on the salt, and as we turn up the strength of the magnetic field, the energy levels split into two, and particles move from the top level to the bottom level. Now these two steps, as I've drawn it, actually happens at the same time as we turn up the field. And the idea is that if you turn up this field slowly, all right, the heat will have time to spread out as the magnetic field is increased, as the spacing between the energy level is increased. So this, and since we are doing it slowly, this gives the heat time to go out and the temperature will stay about the same. So that's why we call this we say that we magnetize it isothermally, or we call it isothermal magnetization. Okay, so that's the first step, that's the isothermal magnetization, and that's why heat is given out. Now, then, what we do is, we are going to demagnetize it. Okay, so when we demagnetize it, let's say from 1 Tesla, I'm going to bring it down to maybe 0.1 Tesla. And when I do that, the spacing between the energy levels will close, because as you see, the energy level depends on the field. If the magnetic field decreases, the energy level decreases. So the spacing between the two levels will come closer together when I lower the magnetic field. Alright, so now I have two levels closer together and I have the particles here. Right? Okay, now this time let's think about Boltzmann distribution again. I've said that we know from Boltzmann distribution that particles at higher energy level there should be fewer particles. Now that I've lowered the energy level, I would expect there to be an increase in number of particles at this higher level. Alright, since the energy level is closer. Okay, so I would expect that I'll get a bit more particles there. But in this method of cooling, we are not going to allow that to happen. And I'll explain why in a moment. We are going to insist that the higher level keep the same number of particles as you lower the energy. How is that possible? Well, that is possible if we thermally isolate this. Let me use the word insulate. So in this step, imagine that we can somehow insulate the salt from the surrounding, right? Prevent heat from going in and coming out. So if we do that, then we prevent particles from moving up or down between the energy levels. Because if you remember from what I said just now, when the particles come down, heat is given out. So if the particles go up, heat has to be taken in. Alright? So if there is to be an increase in number of particles at the higher level, it means that particles must go up from the bottom level. It must take in heat. So if I isolate it thermally, if I insulate the thing and I don't allow heat to come into the salt, then I prevent particles from going back up. So in this way, I can keep the same number of particles at the top. So that's the trick. But what does this mean to the temperature? What does this mean to Boltzmann distribution? In fact, let's have a look at the Boltzmann distribution. It goes something like Ni is equal to A e to the power of minus E1 EI over K BT. So that's the Boltzmann distribution formula. Okay, now the energy here is given by mu B times B. So let me make that explicit minus mu b times b. So that's the formula. Now, in this step, I demagnetize it, I reduce the magnetic field, so that means that the B here decreases. Okay. Now, by insulating it, I have insisted that the number of particles at each level remain fixed, so that this number here remain fixed, doesn't change. So only the B changes. So what happens now is that because we force the N to be fixed and we make the B decrease, in order for this equation to remain true, the T there must change. Alright, and it must change in such a way that N, the number of particles, remain fixed at each level. So since B decreases, that means that T must also decrease, so that B over T remain the same. So therefore, the very act of insulating it and demagnetizing it caused the temperature to drop, and that is how we achieve a cooling effect. So that gives us a simple physical idea about why we can, why and how we can do magnetic cooling using a paramagnetic salt. Okay. Now the next thing I want to look at is how we can estimate the new temperature. So for example, if I have a paramagnetic salt, okay, just draw a lump of salt here, so we have something to look at. Now, suppose that in the beginning, I have a certain magnetic field, say I for initial, and let's say the field is 1 Tesla. Okay, and suppose that in the beginning, initial temperature Ti is 1 Kelvin. And suppose that I go through this process of magnetizing it magnetizing it isothermally at the same temperature, and then I demagnetize it adiabatically with the insulation, and it cools down. What is the new temperature? So the question is, suppose that the final magnetic field, when I demagnetize it, is, let's say, 0.1 Tesla. So initially, of course, we start from 0 Tesla and then we magnetize it until 1 Tesla, and then we demagnetize it down to 0.1 Tesla. The question is, what is the final temperature? Now, there's actually a simple way to calculate this. And to do that, let's go back to the expression for Boltzmann distribution. So that's really, let me just focus on, say, one of the level to make it easier, the higher level, and 2 is the number of particles there, and that's the Boltzmann distribution. So the idea is that when we do the demagnetization, as we demagnetize it, because we have isolated it thermally, so number of particles at each level cannot change, so therefore B over T must remain fixed. So that's what we saw just now, and in fact this gives us the formula that we need to find the final temperature. Okay, if B over T is constant, what it means that in the beginning, alright, when I have these two, this field and this temperature, the B over T is Bi over Ti. Now after demagnetizing, the B over T would be Bf over Tf. That B over T must be constant just means that those two fractions must be equal. And there we have the formula that we need. We know Bi, Ti and Bf, Bi, Ti and Tf, and therefore we can find Tf. Okay, you plug in the numbers and find the solution. Now of course, because the numbers here are quite simple, we can also do it mentally. Right, we can say that, okay, the ratio of B to T must be a constant, or we can think of it as that B must be, or T must be proportional to B. So in this case, we started with a temperature of 1 Kelvin and a magnetic field of 1 Tesla. And now the magnetic field is decreased to 0.1 Tesla. That means it has decreased by 10 times. So since B and T are proportional, therefore T must also decrease by 10 times. So 1 Kelvin must decrease to 0.1 Kelvin. And that's the answer. And so now we have a simple, very simple way to find, to calculate the final temperature. Okay. However, there is a problem. Let's look at this formula. So this formula tells us that that temperature, that T is proportional to the magnetic field, which is why, as we now understand, we can, by lowering the magnetic field, we can lower the temperature. Now, what if I simply switch off the magnetic field, so the magnetic field lowers all the way down to 0? So according to this formula, if B goes to 0, T should go to 0. Now, so it means that all I need is to switch off the magnetic field completely, and T becomes 0 Kelvin, and we can achieve 0 Kelvin just like that. And that's really simple. But unfortunately, it doesn't happen. Right? First, because we know that 0 Kelvin, from what we understand from thermodynamics, 0 Kelvin cannot be achieved. Although there will always be new technology in the future and new physics that we do not know yet, but for now, 0 Kelvin cannot be achieved, and that means that we have a problem. It means that this equation, there must be something not wrong, but there must be something more to this equation. Alright, this equation must not be the complete story. It probably means that when B becomes smaller and smaller and the temperature becomes smaller and smaller according to this formula, something happens, alright, something different, something new, alright, something we have not thought of happens at this very low field and energy. Let's think about that. I'm going to magnify, really magnify that lump of salt so that we can see some of the atoms, right? At least in our mind. So suppose that these are the ions in the salt that have the magnetic moments. So these are tiny little magnets. Alright, so in the absence of an applied field from outside, all these tiny magnets will point in random directions because of thermal motion. Alright? And of course, when we apply a field, when we take a magnet and put it next to this salt, a lot of these will start aligning themselves along the magnetic field. Now what I want to do here is to understand what goes wrong with this formula. Right? Something happens that prevents T from going to 0 when the external field B goes to 0. Now if you look at this picture, let's look at one of these ions. Okay. Now if there's no, what happens if there's no external field? Alright, if I remove the external field completely, this is all I have all these ions, and if I look at that particular ion, now you see that this ion, this tiny magnet have tiny magnets around it. Okay, and once we think about the tiny magnets around it, we realize that those neighboring little magnets must produce magnetic fields as well. Tiny field, but they're there. So each of these would have little magnetic fields around it, and that one will have magnetic fields around it. So if I look at a particular ion, this ion, it must surely experience some magnetic field from the surrounding ions. So you can think of this as a residual field, or just the neighboring fields. So there would be some magnetic field here, maybe a tiny amount. I'll call it little b. Okay. Now let's call the magnetic moments of each of this tiny magnet. Let's call it mu. So this is the answer. The answer is that we can never reduce the field on each ion to 0, to complete 0, because there's always this remaining field from the surrounding ions. So the B there can never go to 0. Alright, when you made this equation, I was thinking of this capital B as the magnetic field that you apply from outside, from a magnet or electromagnet. Alright, but in reality, this is not the only field acting on each of the ion. There is, right, if you have a strong magnet, most of the B here would be from the external magnet, but a tiny bit will be from the surrounding ions. And when we switch off that external magnet, or just take it away, and there's no more applied field, there is still a little bit of the surrounding field that remains. And it is that little field there that prevents the field from ever going to 0, and therefore the T there will also never actually go to 0. Okay, so what this means is that this equation becomes inaccurate at really low magnetic field and has to be modified. Now the usual way to modify this is to replace the B there by, well let's say one simple way to modify it would be to replace the B by, say, B from the external field plus a little B from the surrounding ions. So that might be one way to modify this. But because the surrounding fields are at random and it can take it can take random values depending on the orientations of the neighboring magnets. Empirically, that means from measurements, it has been found that it is better to use this expression. Okay. Now, so we shall not go into why this particular expression, but for our purpose, we just need to know that it gives us the correct value when the external field goes to 0. See, because when the external field goes to 0, big B becomes 0, and the square root of B squared is just B. It's just the remaining field from surrounding atoms, which is correct. Okay, so what this means is that instead of using this expression, we now use this over T is equal to a constant. So that is our corrected and more practically correct equation that we can use to estimate the final temperature. Okay, so that seems alright, except that now we have another problem. How do we know what B is? That's our next problem. Now there is a way to estimate B. In order to understand this, let's think about the idea of a paramagnet. Now I've called this a paramagnetic salt. So what exactly does this mean? What does it mean to be paramagnetic? And how is it different from the normal magnet that we use in everyday life? Right, the two little iron bars that stick together when you hold them close. So there's this idea that this is paramagnetic, and then there is the more familiar magnets that we use in everyday life, the little iron rods with North Pole and South Pole, which are ferromagnetic. Now for a start, our familiar little piece of magnet with the North Pole and South Pole, now that is a piece of magnet because all of the, or most of the iron atoms in a piece of magnet, right, this piece of magnet, the magnetic moments in all the atoms align themselves in the same direction, and this is align themselves without the need of an external field. Their own field is strong enough for all the magnetic moments, all the atoms to align themselves so that the whole thing becomes a magnet. Whereas in a paramagnetic salt, if I consider a lump of salt here, I have the ions in this salt, all of them have little magnetic moments, but the magnetic field is not strong enough to for them to align themselves. So that's why a paramagnetic salt is not on its own, it's not magnetic in the sense that, well, let me take that back. A paramagnetic sword it does not act like a piece of iron magnet. It does not attract things directly. Alright, one lump of paramagnetic sword does not attract another lump, simply because all the little magnetic moments in the atoms are randomized. There's no alright, they all cancel each other out. So we have these two types of situation. Right. Now, paramagnetic and ferromagnetic materials, we can actually understand the connection between them. And what connects them is temperature. Now, I've just mentioned how in a piece of ferromagnetic material, like the iron magnet, how all the atoms have the magnetic moments aligned in the same direction. So instead of randomized like that, they're all pointing in the same direction. Now imagine what happens if I put this piece of magnet in a fire, really hot fire, right? That will start shaking up the magnetic moments, shaking up all the atoms, and when the temperature is high enough, the magnetic moments in the atoms, right, they start pointing in more and more random directions until above a certain temperature, all the magnetic moments will become randomized, and this piece of magnet would stop being a piece of magnet. It would lose its magnetism. And in fact, that's how we learn in high school, as a method of demagnetizing a magnet by putting it over a fire or by hammering it with a hammer. Alright, you can actually demagnetize it. Alright, it's because in a fire or when you hammer it, you are randomizing the directions of all the atoms, or of all the magnetic moments. Now, and so when you heat it above a certain temperature, they become randomized, and that means that they become the piece of iron becomes a paramagnet, right? Simply because it now fits this description that the magnetic moments are randomized. Okay, so in other words, a ferromagnetic material becomes a paramagnetic material when the temperature is high enough. Conversely, let's look at our paramagnetic sword that looks more like a lump of salt that you have for lunch or dinner. Okay, our lump of salt here looks nothing like this piece of iron magnet. But using this same reasoning, right, about raising the temperature, or a similar idea, let's imagine lowering the temperature of this paramagnetic sword. So if you think that, right, all these magnetic moments are pointing in random direction because the temperature is too high, then if we lower the temperature, the thermal motion decreases, right? The movement becomes less and less. So eventually, below a certain temperature, there will be so little motion that it is possible for the magnetic field from surrounding atoms to align all the magnetic moments so that all of these little magnets start to point in the same direction. Okay, that would happen if there's no more thermal, or there's very little thermal motion to disrupt the arrangement. So once that happens, once the surrounding field can start aligning themselves, aligning the moments themselves, this lump of paramagnetic sword becomes ferromagnetic. It would start acting like a piece of iron magnet. So that's the connection between the para and the ferromagnet. Now, while we are here, let me define a new symbol, Tc. And Tc is called the Curie temperature. Alright, the Curie temperature is a temperature above which a ferromagnet becomes a paramagnet, or below which a paramagnet becomes a ferromagnet. So that's the Curie temperature. Now, what has this got to do with all this, the magnetic cooling that I was talking about? Now, if you think about the whole idea of the magnetic cooling that I've described, it relies on the property that in the beginning, not just in the beginning, but through the whole process, the orientations of the magnetic field, they are randomized. Alright, they are all random. In the beginning, they are completely random, same number pointing up and down. But when you apply a magnetic field, alright, more of them start pointing in one direction, some still point in the other direction. Okay, but they are still randomized by the temperature, so that's why they obey the Boltzmann distribution. Okay. So that's how it works. It works because the cooling method works because in this paramagnetic material, the temperature is much higher than the Curie temperature. Alright, so that it's a paramagnet, and so that the magnetic moments cannot align themselves. Right? Now imagine what happens if the temperature, if I lower the temperature, if I can cool down this lump of paramagnetic salt until it goes below the Curie temperature. If that happens, the paramagnetic salt becomes ferromagnetic, and then all the magnetic moments would start aligning themselves. And if that happens, the magnetic cooling will stop working, because if the magnetic moments can all align themselves, then they will all be always pointing in the same direction, like in this piece of iron magnet. And if they are all pointing in the same direction, then it's not going to respond to my magnetization or demagnetization and all those other things that I wanted to do to the paramagnetic salt, alright, to make it cool down. It's just not going to respond to any of those. It's just all going to point in the same direction all the time. So it just would not work when you try to use it for magnetic cooling. So that's why it will only work when the temperature is above the Curie temperature. Alright, then it has this behavior of this random directional behavior of that we have seen. Right, so this understanding, okay, this picture here brings up a new issue, if you like, for paramagnetic cooling. Right, it brings up something new. It means that it is not possible to cool a paramagnetic salt, or for magnetic salt to cool down below its Curie temperature, simply because it doesn't work anymore after that. So what we have therefore is a lower limit to the temperature that can be achieved by this cooling method, and that's the Curie temperature. Now, for example, in typical paramagnetic salts that has been used for magnetic cooling, the Curie temperature tends to be a few millikelvins. Right? For paramagnetic salt, the Tc is of the order of millikelvins. A few, maybe between 2 to 10 or thereabouts. So alright, and this gives us a physical limit for the cooling method. So cooling really cannot go below this. Okay, so let me say, for example, let me just take 1 millikelvin as an example. Now this is something that can be measured and has been measured. So taking this as an example, we can use this to estimate a value for this residual magnetic field, the field that it's experienced, the field from the surrounding atoms that that a particular ion will experience. And the connection between Tc, the Curie temperature, and the magnetic field is, let's see, you can think of it this way. This magnetic field, B, times the magnetic moment, alright, mu B is the magnetic energy, right? That is like the magnetic energy level that we have seen earlier. So the magnetic moment times magnetic field gives us the magnetic energy. Now, the thermal energy, if you are at this particular temperature, is Kb times Tc. So this is the expression that we have seen from statistical mechanics. This expression gives us the average energy of the particle in a typical system. So Kb times Tc in this case. So at the Curie temperature, we can think of it as the temperature at which, well, at a particular temperature, the kBt is the average energy of the particles. So when it's Tc, that will be the average energy of those particles at the Curie temperature. Now we can think of the Curie temperature as a temperature in which the particles, or above which these particles have enough energy to overcome the field from the surrounding magnet. Alright, because you can think that the surrounding fields from the surrounding magnet would try to align this atom, but if it is above the Curie temperature, the thermal energy is enough to allow it to randomize itself, alright, to overcome the surrounding field. Okay, and mu B here is, if you like, the energy, the potential energy, alright, that results from the surrounding field. It's a kind of attractive force that tries to align this. So above this temperature, the atom is able to overcome that attractive potential and start to become randomized. So therefore, at the point where this happens, at the Curie temperature, we would expect the two numbers to be just equal. And this gives us a way, alright, it will be just approximately, of course, we're doing it, making an estimate. And this gives us a way to estimate B. Alright, now the mu here would be, okay, we can make use of what we have for the expression that we had for the two energy levels that we saw just now. So it would be roughly correct to call this mu B for the ball magneton, right? Because in the expression we saw just now, mu B times the magnetic field is the energy of, gives the energy of each level. Okay, so taking this as an estimate for the magnetic potential energy, we can then, since we know that the value for mu B, the ball magneton, we can then solve for B. Now if I take the Tc to be 1 millikelvin, we know mu B and Kb, and this would give an answer of let me take this to be 2. something that I've calculated already. So this would give this residual B of about 0.003 Tesla. So a very small field that we have here. Okay, now let's put in some numbers to see what this means for an actual cooling example. So what we had was a residual field of say 0.003 Tesla. Now imagine that now I have this lump of salt. Okay, let's say right. Let's say this lump of salt is within a liquid helium bath, so that it has a starting temperature of Ti equals to about 4 Kelvin. Okay. And suppose that it is in a magnetic field, or we have magnetized it using a magnetic field of 1 Tesla. Right. So now, I want to cool it down. I will demagnetize it adiabatically, and I'm going to bring this field all the way down to 0 Tesla. And remember, this is the external field. Right? So there would be this residual field remaining from the surrounding atoms. So actually, the actual field on each atom would be about that value. So what happens when I have reduced the external field to 0? Okay, the temperature will go down. Now it will go down according to this formula, that V over T equals to a constant. Okay. So we would expect T, the temperature, to go down by a factor of a factor that corresponds to the ratio between these two fields. So let's see, you can do this in many ways. Now what I've done is that I have calculated that V over B, okay, that's T, that's B, I'm doing a different calculation here. I've calculated that the ratio of the initial field, 1 Tesla, to the residual field, that is about 670. So that means that if I reduce the initial field of 1 Tesla all the way to 0, because of the residual field, I would have reduced the field by a factor of 670. And this means that the initial temperature of 4 Kelvin would decrease by that number of times. So the final temperature, T final, would therefore be the 4 Kelvin divided by 670, and this gives six millikelvins. So this is the answer for this particular example. We'll stop here for this session.